Let's talk about the DSA family. So we have two parts, the 6402 and the 6403. Both of those parts were defined and designed to be backward compatible with two offerings, or actually three offerings, from Qorvo, P-Semi, and from our friends at Renesas. So where to start? Again, we define these parts to be compatible. So they come in 3x3, 4x4 packages. They're like any of the DSAs on the family. They're quarter dB step components. They reach up to 31.75 dB of range, and they cover basically down to DC 50 megahertz or so, all the way up to about 6 gigahertz. And most of our customers are using them for around 4 gigahertz and below. So it fits in that nice niche, especially for things like 5G infrastructure. Some customers use it for automotive, for compensators, also for residential as well as commercial type of boosters and repeater applications. So like I mentioned before, they were designed to be backward compatible with other products that are in the market today. And so the one offering, the 6402, that part is the smallest footprint. So it supports a SPI only interface. So with its serial interface, it does add 3 address bits. So you can hang up to 8 of these devices using one common SPI bus, and more importantly, one common SPI enable pin. So with that one pin, because you have the address bits, you can hang in 8 of these parts with just one I/O from the micro. And then of course the same SPI bus. The 6403 adds to that a parallel interface. So there are some customers that want to buy a single part that supports SPI as well as parallel, and that way they can use that one part in their AVL or on their AVL for different applications. If they want that parallel interface for whatever reason, they have the latitude to use that same common device. So the key difference is a little wrinkle we added, and that is what we call RFA, or rapid fire attenuation. Now, in the past life, when I used to work in cellular doing designs for receivers, a common trick that we would do is we would throw in customized levels of attenuation in line, basically to protect the back end of the receiver itself. So imagine if you have an in-band blocker that you cannot filter out, that would come screaming through your receive lineup. And in effect, it would saturate the A to D. And once that saturation occurs, it's game over. You can't receive any of the near or close type of subscribers, as well as the far, of course. So what you do to compensate for that is you throw in attenuation. You basically knock the gain down so you don't saturate the back end A to D. And so you do lose those subscribers that are far away from the base station, but at least you can get some receive signal in that's usable or meaningful. The parts, instead of just supporting one register for the attenuator, we have 2. We have a primary as well as a secondary attenuation state. So when you go and you go through the provisioning stage during a power on reset, you'll send in one SPI transaction to set that primary attenuation state. Then you can send in a secondary one. And why that's useful is we grab one pin. It's a ground pin used by our competitors. You can use that pin as a toggle to flip-flop between this primary and secondary mode. So again, for the blocker scenario I outlined before, you would normally run the part at, let's just say, I don't know, I'll make up a number, 3 or 4 dB. And then when the blocker comes in and you detect that, you want to quickly throw that attenuation in. So you just have the micro flip that one external bit or control line, and you can throw in like 18 dB of attenuation, or up to 31 or 31.75 dB of attenuation. So that's the beauty of that one feature. Now, of course, the parts work very well as attenuators outright. They have, in addition to that quarter dB step, they're glitch-free. So the overshoot and undershoot has been tampered down or well contained. That's important for applications that use DPD loops. The other big feature is the INL and DNL is excellent, especially for the lower end of the range, like 4 gigahertz and below. The INL and DNL are very well contained. The key advantage is that it's a hybrid control mechanism. So with a SPI interface, you get the simplicity, if you will, of having a limited number of control lines coming from your micro. The speed function is affiliated with the parallel interface, right? If you've got access to all 7 bits, you can quickly toggle those on and off to select a custom attenuation set. What the 6402 and the 03 family bring with this rapid fire feature, it's kind of a best of both worlds. You get that simplicity of the SPI control, or the SPI programming, if you will, and you get that speed of the parallel interface with at least 2 attenuation states, or for those 2 states. So again, I talked about this earlier, you can flip-flop between the primary and the secondary. So as fast as you could do that with a parallel interface, you can do it with just 1 control pin. So in terms of key features for the family, in terms of frequency range, it's always where we want to start. The parts are rated from, again, 50 megahertz up to 6 gigahertz. Most customers that we've addressed or have come across tend to focus on that 4.2 gig and below. A lot of applications include repeaters and boosters, cellular infrastructure. We're finding now pockets or more demand coming in from military, aerospace, SATCOM applications, a whole gamut there. And where the parts fit in well there, it's not just in the range. The small step sizes are critical. Be able to fine tune or pinpoint the desired attenuation range. Other key features, I talked before about the INL and DNL performance. So INL is the integrated nonlinearities. Basically, it's the gross attenuation error that you have as you step through the different stages or the different attenuation states. So if you're measuring, you want 10 dB, you're really measuring 10 dB through, or 25 dB, or whatever it may be. That's the INL. It's the absolute error, how far you are off the true, or what you're targeting to be for a true attenuation state. DNL, it's discrete, step-by-step nonlinearities rather that you would get. And again, that's very well contained. So as you move from every quarter dB step, that attenuation error is very, very small. Other key features, the overshoot and undershoot, it's glitch-free, as we use in the phrase for marketing. It basically states that the overshoot and undershoot is well contained. So as you move from state to state, there's always this transient mode that happens where the attenuator, it'll basically give you a little bit more, a little bit less attenuation instantaneously, or for that small fraction of time. So we took special care, if you will, to design that so that that overshoot or undershoot is minimized to the best that we could do. And it's leading in terms of all the other competitive parts that are out there. So again, that's a key feature for people that want to use this in, for instance, a DPD loop. Is when you can imagine as you step through and have those state changes, that wreaks havoc on the DPD loop. The attack time gets all messed up. So if you can contain that, it makes things easier for the DPD itself. So other features, again, it's pin-for-pin compatible, a lot of drop-in parts that we're going after. And yeah, we have 2 offerings. So if you want the parallel interface, you can bring that with the 6403. Usually, the first thing that customers ask are, what can it go any higher than 6 gigahertz, or where does it start to fall apart? Now, in the marketing realm, we've been trained to say, well, the part, it degrades gracefully as you push further and further in the frequency domain, and that is true. The part will start to roll off over 6 gigahertz. The more or less the INL is what takes the biggest hit. It's still very usable. It just starts to become just becomes less tenable, I guess, in terms of accuracy. What we interestingly found is that when we took this core, we started to marry it up with our amplifier family. So the new parts we offer, the 6411 and 6412. When we packed that same footprint with the amplifier, we ended up pushing that die for the DSA into the corner. And by doing so, the lengths of the bond wires were shortened. And luckily, for us, the performance actually got better, especially as you move beyond 6 gig. So we're now at 8 gigahertz. Oh, from the marketing side, they're perfect parts. No, in all seriousness, they are good devices. We are getting a lot of traction with these cores. I talked about the frequency limitations. Ideally, I like to start pushing parts higher in frequency up to X-band and beyond. And that would be it. But as a jelly bean part for a good catalog type of device, a general purpose core, they're very solid. And the volumes that we've had on this core, they're very popular for automotive applications. One thing I didn't mention, we do have an automotive qualified variant that's 6402W, and that part's rated up to 105C. The cores themselves, the basic ones, are actually rated up to 115C. So another positive or another attribute to tout. Yeah, other than again the I and L falling off, that's the biggest holdup. Insertion loss, in an ideal world, the insertion loss would be a little more, would be less basically as you move higher to frequency 2. That I know becomes a bit cumbersome, and we're trying to compensate for that with some of the new DVGA offerings where we add in that gain to offset the loss. And also we're looking at adding gain slope. So as the attenuator starts to become lossier as you go higher in the frequency, we're looking to compensate that with gain from the gain block. So with the 6402 and the 6403, one of the things that we did, we created the EVB. We ended up adding this Adafruit little daughter card, right? These are off-the-shelf parts that we picked up. You can buy them, I believe, on DigiKey. I'll look at Mauser. They're readily available. And basically what it allows you to do is you can use a SPI interface. This version uses a USB-C connector. And from that, we have a little GUI. You just download the GUI onto your laptop, and you can program it up for serial or parallel mode. You can then send whatever SPI transaction you'd like. You want to set it for whatever attenuation state, or if you want to be able to trigger the rapid fire function. The Adafruit has a set of controllers on it natively that allow you to program virtually any pin on the O2 or the O3. It comes as a complete set. It wouldn't do you much good to look at just the device without any programmability. So get it from us. You just go to the product page on our website and look under the applications sub-tab, and you'll find it right there.
Thank you so much for watching. If you'd like more information, please email us at sales@guerrilla-rf.com. And don't forget to subscribe to our channel for more content from Guerrilla RF.